All right, so uh, the plan for this is that I'm going to do a live solve of the practice test 3, and I'll upload the video as well as a version of this, I guess a printout version of this. But I also am planning to prepare a typeset version of the solutions so that the typeset version should be cleaner, and in doing so, I'll be able to check if there are any mistakes that I make in the live solve, and then most likely any errors that are caught, I'll put it in the description in the video, and you'll be able to compare the live solve version versus the typeset version of the solutions, so, to note if there are any discrepancies. Okay. Right, so this is solutions. Maybe I'll say okay. So I've only briefly glanced at the problems, which means that it's gonna take me a few seconds to figure out how to proceed with some of these problems, perhaps, and there can be errors, so do be aware to don't completely take what I say as correct until, like, I guess the very end of this process. All right, so first we integrate this function um, over this region bounded by y equals x squared and y equals x plus 2. So the first thing I want to do, okay, so to me this looks like it's talking about a two-dimensional integral. I want to depict what this shape is, so certainly it's a parabola, but I'm thinking there might be multiple intersection points that can happen. So let's see, at 1, at 2, 3, 4, at 1, 1, 2. So at 1 we have this point, at 2 we have the 2 comma 4, minus 1 comma 1, minus 2 comma 4, tracing out the parabola. Okay. The line is going to give you, maybe I'll use a different color. The line is going to give you this point, 1, up 1, over up 1. So there's the point 2 comma 4 in common, and there's going to be the point, what is that, negative 1 comma 1 in common. So the way that you could have seen this algebraically was you set the two equations equal to each other and you solve, and that'll give you the roots. That'll give you when these two curves equal each other. So x squared minus x minus 2 is equal to 0. You could then factor this. This is x minus 2x plus 1 equals 0, so therefore x is equal to 2 and negative 1 are points where these two curves intersect each other, which we are also see in this figure that I've depicted. And so shaded in red is the region that we're supposed to integrate. So the problem asks us to integrate. It's going to be a double integral. Let's call this region D, just so that I have something I can refer to. Call that region D. So we integrate over the region D the function f. So in general, it'll look like this. Now, filling in precisely this function, it's the function x. We can do this. So this region, it's not a type 2 region. It's a type 1 region. So notice that if we try to express this so that the outer integral was with respect to y, we'd have an issue here. It would require us to chop this domain D into two parts, and then we'd have two separate integrals. So it's preferable to treat this as a type 1 region. You integrate with respect to x on the outside and with respect to y on the inside. So integrating with respect to y, we have, well, okay, let's start with the x. So the x ranges from minus 1 to 2, and the integral with respect to y goes from the lower function, which is the x squared function, and it goes up to the upper function, which is the line. So that's x plus 2. So this double integral is integrating over the entire domain D. Right? You can kind of tell that based on the bounds of the integral. And we're integrating the function x. Okay, so let's go ahead and do that integral. So notice that because this is not a rectangular domain, we can't just split it apart. This has to be treated as an iterated integral. If we integrate this with respect to y, the x will be pulled out, and we're just integrating the function 1. So that's just going to be the value. The integral of 1 is just going to be y. You would evaluate at y is equal to x squared, and at y is equal to x plus 2 dx. You don't need to show this step. This is just me trying to show every little step in case there's any confusion. Okay, doing this evaluation, we end up with x plus 2 minus x squared dx. Now let's simplify our integrand. Let's put it in polynomial order. So we have a negative x cubed plus x squared plus 2x. We integrate all of this with respect to x. So now that's negative x to the 4 over 4 plus x cubed over 3 plus x squared over 2, but the over 2 is going to cancel the 2. And then we evaluate from minus 1 to 2. Alright, well, the evaluation is not too bad. That's fine, I'll just do it. So 2, 4, 8, 16, so negative 4 plus 8 over 3 plus 4 minus, plugging in at minus 1, this becomes negative 1 over 4. Right, the negative 1 raised to the 4 becomes plus 1, this negative still hangs around. You have minus 1/3 and then plus 1. Okay. Well, so simplification there. Let's see, what else can we do? Get rid of that dot there. What else can we do? 8 over 3 plus 1 over 4 plus 1/3 minus 1. So that's 9 over 3, so this is just 3 minus 1, so we get 2. So this is actually 2. So I'm just pointing out that these two things combine together easily. 2 plus a 4th, so that ends up being 9 over 4. Okay. This is one of those things where I would want to double check my calculation with Mathematica. I will save that for maybe the end. Well, I don't know. This is not too bad if I actually show you how that works. So, so with Mathematica, it would just be, I can just immediately type this in. X from, let's see, y from minus 1 to 2, and x from, other way around. X from minus 1 to 2, y from x squared to x plus 2. 9 over 4, good, okay. I know that I can always potentially make arithmetic mistakes, so I just want to be super careful, just in case. All right, let's see, 2a. We're given this, okay, this region. If you were integrating over R, would you integrate with respect to Cartesian, polar, cylindrical, or spherical? Explain why, and express the bounds in that system. Or, yeah, okay, in that coordinate system. So, well, because we have a z here, this is going to be a three-dimensional system. This region is being described in, it's a three-dimensional region, so we definitely aren't talking about polar. And this description really makes me think that this should be cylindrical. So I'm thinking cylindrical, and it's to do with the fact that, well, okay, so this looks like an r squared. less than or equal to z, less than or equal to 4. So it seems like we have this series of inequalities. These two conditions are fixing what part of the theta. So x being positive, y being negative means we're talking about this region there, which tells me that this has theta going from, I would describe this as minus pi over 2 to 0. Minus pi over 2 to 0 is this quadrant, this the fourth quadrant. Okay, but now coming back to this, so z between 4 and r squared. So kind of the profile view of this, not r squared, just r. The equality is z is equal to r squared, and z is at most 4. So what that set means is that r is at most 2. Right? And it is certainly the case, I can see that, oh, I shaded the wrong part, actually. Didn't mean to shade that. So this is the parabola. This is z is equal to r squared. And we can get, we can see from this picture that r is between 0 and 2. But we want z to be greater than r squared. So that is actually shading this part of the region. Okay. And so this now allows me to visualize what this region R actually looks like. It's take this domain and then rotate it about the z-axis. And so this ends up being a paraboloid. Well, I guess the paraboloid would be if this was hollow, so it's like a solid paraboloid. It includes the interior. There's this outer portion which is parabolic, and then there's this top which is a flat circle. And so, yes, this really makes me think that cylindrical is the sensible coordinate system to use. And for z, so the bound for z, you can notice that it depends. Above is so above is constant for z, but below it depends on r. So I would write it like this. So the bound for z depends on r, which means that when we set up our integral, we'll have to force the z integral to be within the r integral. Okay, let's see. So to answer this part of the problem, explain why you chose this. I don't know. You can probably write a few things. I narrated a lot of these things, so it's definitely 3D because there's a z component, and flat top, I guess, is one way to think about it, which to me implies that cylindrical better than spherical. But that's a heuristic. Okay. I can imagine that there are some very weird problems where initially it looks like cylindrical is better, but then like for whatever strange reason, spherical ends up working better. So you do have to be careful with these types of problems and try things out sometimes. But for here, I'm fairly sure that cylindrical will be better than spherical. Expressing the bounds for R in that system. So I'm gonna take that to mean, so in effect I did already write that because I've written it here with r bounded, z bounded, and theta bounded, but just to make the answer more clear to the viewer or the grader, let's write it in set notation. So we can write, which is similar to, like, I don't know how the homework and the lecture notes have written these things. So R is the set r theta z, where, let's even switch it over to using inequalities instead of the interval notation that I'm so comfortable with. Okay, I'm already doing it wrong. Minus pi over 2 less than or equal to theta less than or equal to 0. 0 less than or equal to r less than or equal to 2. And also z between r squared and 4. Okay, so that is how I would express the bounds for the region R. Right, so now part B, find the volume. So as you can recall, the volume can be computed using the integral over the region. So we're talking about the triple integral of the function 1 over the region. So one way to express that, volume of R is the triple integral over R1 dv, the volume element. Now let's spell out what that triple integral actually is. Give myself a bit of space. So it's still the function 1, and I think I want to do it in this order actually. So minus pi over 2 to 0. The outermost guy is d theta. The next one ends up being 0 to 2 dr. And then we have r squared to 4 dz. Okay, and you can see that we indeed have the z integral within the r integral. Okay. Now to compute this thing. So before I treat this as an iterated integral, I want to note that we have a coupling between z and r, but theta is perfectly fine to actually split out, right? This double integral within the theta integral is actually independent of theta. So we can actually, if we think of this as a function, this double integral, if we think of it as a function of r and z, we can then pull it completely out. Of the theta integral. So then we end up evaluating the theta integral like that, and then product it with the double integral, which we can't do anything about, r squared to 4. Again, the function 1 dz dr. Okay. Well, this integral is easy to compute. This is just the length of this line segment from negative pi over 2 to 0, so that's just going to be pi over 2. This integral, well, we need to do a bit of work on that. So integrating that is going to give me z evaluated from 4 to r squared, which is clearly going to equal, so I'll say that is going to end up equaling 4 minus r squared. We then integrate that with respect to r, giving you 4r minus r cubed over 3, evaluated from 0 to 2. Multiplication there, pi over 2. So plugging in at 0 is just going to be 0. That's nice. Plugging in at 2, we get 8 minus 8 over 3. And lastly, I'm going to want to simplify this. So I can pull out, I guess there's a few ways of thinking about this. I would rather pull out the 8 here and then think of this as 1 minus 1/3, giving me 2/3 here. And then when I pull out the 8, it's going to cancel with the 2, leaving me with 4 pi. Okay, and then in total, this is going to be 8 pi over 3. You don't have to arrive at it through this kind of stranger way of doing the arithmetic. You can just compute this guy. I factored it out just because it's a bit easier to think about this. Instead of, 24 over 3 minus 8, 16 over 3 divided by 2. Yeah, okay, it's the same thing. Right. So we get 8 pi over 3 for this answer. Do I want to double check that? Yeah, I'll double check that off to the side. Integrate 1 theta from minus pi over 2 to 0. R from 0 to 2, z c from r squared to 4, 8 pi over 3. Good. Okay, continuing. Find and classify all the critical points. All right, so that's where we use the discriminant to classify. To find, we set the first derivative equal to 0. And in this kind of two-dimensional setting, the derivative, by the derivative, what I mean is the gradient. So first, just to make it a bit easier to kind of name things, let's just call that guy f. Okay, so the critical points we'll find by computing the gradient of f. So that's the x derivative and the y derivative. As you can see, this is only of two variables, x and y. All right, so the x derivative. The x derivative, this term is going to give me a 6xy minus a 6x. Yep. And then the y derivative is going to give me a 3x squared plus 3y squared. Nope, not that term, but this term. Minus 6y. And we set all of that equal to 0 to solve for the critical points. Okay, so that gives us the system. So this guy equals 0, which I'm already beginning to factor in my head. So we have y minus 1 equals, so 6x gets factored out, you get a y minus 1 is equal to 0. And you also have the system where this is equal to 0. Not sure if there's anything clever I can do with that just yet. I'll just write it. Okay, so the critical points are the points that satisfy this set of equations. Well, the first equation immediately tells you that x is equal to 0 or y is equal to 1. And then with that, let's try to see what happens to the second equation. So if x is equal to 0, then this equation reduces down to 3y squared minus 6y equals 0, which implies, so I'll factor out a 3y, we get a y minus 2 equals 0, which means that y is equal to 0 or 2. So this has given us 2 points, which I'm going to use a different color so that it's easier to see that. So when x is equal to 0, we end up with these 2 points. So this contributes the critical points, the critical points 0, 0, and 0, 2. Okay. On the other hand, if we had this other branch, if y was equal to 1, then, well, let's see, what does this reduce to? 3x squared, so if I plug in this, it's plus 3 minus 6 equal to 0. Yes, that's right. So then, 3x squared minus 3 equals 0, and so 3x squared minus 1 equals 0. Okay, so that means that x is equal to plus or minus 1. Which contributes, looks like another 2 points. Okay, so we have the point 1, 1, and we have the point minus 1, 1. So these are all of the critical points for this function. Yeah. Perhaps I should also mention that, technically speaking, there are other critical points that can arise if the gradient is undefined, but this function doesn't have any such points. It's a polynomial. And it would be really weird if you're given a problem that has these critical points where the function, where the derivatives are undefined. That would be pretty bad, and I wouldn't expect you to have such a problem. Okay, so we have these 4 points. That's finding them. We found them. Now we have classify. So in order to classify them, we need the discriminant. So let's compute the discriminant now. I have the first derivatives. I'm going to need the second derivatives. So the xx derivative, let's see what that is. So this is f sub x. The x derivative of that is going to be 6y minus 6. And maybe for plugging in purposes, I'll factor out the 6. Okay. Let's do f sub y. So that's going to be 6y minus 6. Really? I'm just going to check that again. Yeah. Yeah, that looks right. Okay, so then 6y minus 1. And then f sub xy. So taking the y derivative of this just gives me a 6x. Okay. And so all together, what this tells me, the discriminant, I think the formula is given to you, but I know it off the top of my head. So yeah, so it's given to you, but if you don't remember, it, then it's given to you. But it's easy enough to remember actually, and all the conditions are given to you as well. That's kind of going easy on you. It's not always given to you in other runs of this class. All right, so let's see. I'll just copy it down. So it's fxx fyy minus fxy squared. And then, of course, you'd be plugging in the specific function, the specific points. Let's write down what this ends up being. So we actually end up getting a y minus 1 quantity squared minus 36x squared. Interesting. I'm not going to bother with factoring out the 36. Okay. So let's classify the critical points. So D at 0, 0. You get a 1 here, you get a 36 minus 0. Okay, so that's positive, which means that we need to plug the point into one of the second derivatives. So technically you could use either xx or yy, but the convention is to use xx. So we do that, and we get negative 6, okay, which is less than 0. So that tells us second derivative, I'm just double checking. So yeah, so it's negative, which means it's concave down, so that means that this is a local max. Okay. At 0, 0. Plug in 0, 2. Let's see what we get. So we get 36 again, I think. Yeah, we get 36 again. Okay. fxx at 0, 2. So I plug in, the y is now 2, so that gives me a 6. That's greater than 0. So that means we have a local min, right? Because this second derivative being positive means it's concave up, which means that that's a local min. So we have a local min at 0, 2. Alright, so now what's going to happen with the 1, 1 and 1, minus 1? We'll just also copy that down, or minus 1, 1. Plugging this in, so the 1 makes this a 0, minus 36. Aha. Yes. Okay. So that means it's a saddle, because the discriminant is negative. And then plugging in at minus 1, 1. So again, the y equals 1 gives you a 0 here, and then this minus 36 1 squared. So yeah, we get a negative 36 again. So we get a saddle at -1, comma 1. This feels a lot like one of the example problems that I gave, but oh well. All right, so that is the classification, and I guess that this is. I would box this. Let's see if this will work. Yeah, very good. Okay, I want to maybe move it a little bit. Okay, there we go. So that's the classification of the critical points. That was what this problem was asking for. Next problem. Use Lagrange multipliers to find the minimum and maximum of the function subject to the constraint. Okay, it's a function in 3 variables. So given that we have a constraint, you should be thinking of the Lagrange well, okay, it tells you Lagrange multipliers. Sometimes problems aren't as nice and they don't tell you what method to use. But yeah, okay, so it does tell you. But the key thing is the fact that there's a constraint here tells you to use Lagrange multipliers. So Lagrange multipliers says we are solving the equation nabla f is equal to lambda nabla g, right? The gradient of f equals to lambda times the gradient of g. This ends up being a system of equations that you then solve. And then you have to tack on the constraint, I guess, also. So it would be like g equals 0. Although one thing that you would do to this constraint, just to set it equal to 0, is you'd move the 1 to the other side. So really, you want to be thinking of this as the function. How do I want to do this? Maybe I'll just write it off to the side here. So you want to be thinking of the function g as being x squared plus y squared plus z squared minus 1 set equal to 0. So Lagrange multipliers is solving this system. And spelling out what exactly that system is, well, taking the gradient of f, that's going to be, so the x derivative just gives me 1. The y derivative gives me 2y. The z derivative gives me minus 1 lambda. And then so I'm thinking about the gradient of f, or g, where g is this guy in blue. So the x derivative gives me 2x, the y derivative is 2y, the z derivative is 2z. And the last part is the equation g itself. So you could write it in this altered form with the minus 1 equals 0, or you could just copy it down as the constraint given. I will typically just copy the constraint as given. But you can see that that's the same as saying that this g expression is equal to 0. Okay, now let's fully expand that out into a system of 4 equations. So this is saying that 1 is equal to 2 lambda x, that 2y is equal to, that's kind of weird, 2y lambda. I'm debating as to whether I should put lambda in front. I think I've been doing that, so let me do that. And minus 1 is equal to 2 lambda z. And lastly, the x squared plus y squared plus z squared is equal to 1. So we have a system of 4 equations and 4 unknowns. The unknowns being x, y, z, and lambda. All right, now let's see what we can do with this. Yeah, so the thing that I found weird was the second equation, so let's try to focus in on that. Moving things to the other side, 2 lambda y minus 2y equals 0, which says that 2y lambda minus 1 is equal to 0. I'm just factoring the 2y out from both terms. Okay, so this gives us cases. This either says that y equals 0 or lambda is equal to 1. Do I want to proceed with that? Maybe. Yeah, so let's try it out. Let's try that out. The case that will reduce quickly is when we have lambda is equal to 1, right? Because that will actually allow us to solve for x and z due to the first and third equation. So according to this, 1 will be equal to 2x, which means that x is equal to 1/2. The third equation is going to be that minus 1 is equal to 2z, which means that z is equal to negative 1/2. And what does that say anything about y? No, y is free. But taking these values and plugging it into the constraint, into the fourth equation, what does that tell me? 1/4 plus y squared plus 1/4 is equal to 1. So that actually fixes y, it looks like. So we end up having a 1/2, which we subtract over. Y squared will be equal to 1 minus 1/2, which is 1/2, which implies that y is equal to plus or minus. I'll write it as 1 over root 2. We take the square root of this guy, and it does appear there's not a constraint on y saying that y needs to be positive or not. So we have these two possibilities for y. So altogether, this has given us the constrained critical points, 1/2 plus or minus 1 over square root of 2 and negative 1/2. So there are two constrained critical points from this branch. I'm trying to make this look a little bit nicer. Okay. Next, let's see. Let me move that up a bit. If instead you have, what was the other case? Y is equal to 0. If y is equal to 0, so then equation 2 here disappears and the system reduces down. I think we'll have to work with the reduced system and see if there's anything we can do with it. 1 is equal to 2 lambda x. This also basically assumes that lambda is not equal to 1. Right? Although I don't think we're going to end up using that. And y is equal to 0 reduces the constraint to x squared plus z squared is equal to 1. So this is our reduced system of equations. What can we do with this? Well, what comes to mind to me is I can solve for x and z in the first and second equation, and then plug the result into the third. So we'll have an expression for x and z in terms of lambda. There's also kind of a relationship between x and z themselves because of this negative. It looks like z is equal to negative x. 1 over 2 lambda is equal to x, according to this. So, yeah, as a comment, this is assuming, right? So the fact that we started to divide means that the fact that we divided by lambda is assuming that lambda is not equal to 0. So if we're being technically, I don't know, pedantic about things, then we would have to split off into the case where lambda is equal to 0. But I think that doing that, is only going to give you the constraint, which I think means that the points there are just the entire boundary sphere, right? This constraint is is the sphere itself. No, that is kind of strange. I might need to think about that later. Let's kind of skip over that for now. So let's just assume we can divide by lambda. Assume that lambda is not equal to 0. So I'll just, in red, I'll write assume lambda is not equal to 0. Okay, so then we end up getting this. And you'll notice that this is equal to negative x. Right, so although we could have substituted these fractions in for x and z and then like solve for lambda in that case, that is kind of the long way around. We would, because if you do that, you'd solve for lambda and then you'd take those values of lambda and then plug them back in to solve for x and z. Instead of doing that, I may as well use the fact that there's a relationship between z and x and just substitute that right into the constraint. So what happens with the constraint, let's replace out the z. So we get x squared plus minus x squared equals 1, which is just saying that 2x squared is equal to 1, which means that x is equal to, well, divide by 2 is take the square root, plus or minus 1 over root 2. Okay, and so this will end up giving us 2 points, right? Notice that for when x takes the positive value, z will take the negative value. It'll be the negative of x. So, so this ends up giving us, well, the way we could write this, we could write it like plus or minus 1 over root 2, 0 for the y-coordinate, and then minus plus 1 over root 2 to signify that there are 2 points here. Right. So when you take the upper sign, it's the plus for the x-coordinate, the negative for the z-coordinate. If you take the bottom sign, that's the negative for the x-coordinate and the plus for the z-coordinate, since x and z are negatives of each other. So you end up having this, these 2 points. I suppose for consistency, let me make this a different. Let me make this the same color. Can I change the color? That may not be the same color. Close enough. All right. Yeah, that lambda equals 0 kind of bugs me. But if lambda equals 0, that's like that's a singular gradient. That would mean that the gradient of f is the 0 vector, which is really, I don't think that tells you anything useful. Okay, the last part of this problem is going to be to plug the points in order to determine the minimum and maximum for the function f. Okay, so unfortunately, I'm sort of low on space. I guess that means maybe I'll move off to this side. Okay, so x plus y squared minus z. F x plus y squared minus z. Alright, I'm just going to kind of abbreviate things. So if I evaluate f on this, we'll get 1/2. The y squared is going to get rid of the sign difference, so it'll just be a plus 1/2 minus negative 1/2 for the z value, which equals 3/2. Okay. All right. Whereas if I plug this, if I evaluate f on these points, well, Okay, the x does make a difference. How am I going to write this? I guess I'll split it into two different cases. So we have root that plus 0 minus negative. So that is 2 over root 2, which simplifies to root 2. Or you have the case negative 1 over root 2 plus 0 minus 1 over root 2, which is going to be negative 2 over root 2, which simplifies to negative root 2. Okay. And just to make comparisons easy, I'm going to do decimal approximations. So 1.4, negative 1.4. Okay. The maximum and minimum of the function. Okay. So from this, we're able to conclude that the maximum is the value 1.5. So the value 3 over 2, which occurs on these 2 points, but we don't need to mention that. And the minimum value is the value negative root 2, right, the negative 1.4. And so that is the answer to this problem. Yeah, the maximum and minimum of this function subject to this constraint. Yeah, so subject to this constraint, these are the max and min of the function. Okay. Number 5. We're inside this region. Okay, so this is a sphere of radius 5, centered at the origin. And this is a somewhat bothersome condition. This y greater than or equal to 0 looks like it's cutting the theta. Okay, so I do have an impression of this, and it might be more from my own experience with things, but I believe this is going to be a spherical cone. Rho squared is equal to 25. In other words, rho is equal to 5. So I'm already thinking that this should be in spherical coordinates. Maybe I'll write that down. Spherical. So this condition is the one that we really need to work with. I can factor out the 3. X squared plus y squared. Okay. So if we were trying to use cylindrical, then we could rewrite this as r squared in the square root. But then we wouldn't be able to use this rho. We would instead have to use r squared plus z squared is equal to 25. Which I suppose is possible. Do I want to entertain that option? R and z, r squared plus z squared equals 25 ends up being a circle. So this ends up describing r squared plus z squared equals 25. And then this relationship, you could think of it as that. Z is equal to negative root 3. R. That's a really weird looking cone if that's the case. Because it's going to go like that. So really, there's going to be some other... It's not really a cone, it's kind of... You subtract off a cone. Okay, so now I see, I think. Somewhere you will have that this ends up intersecting with this this line. So this is the line z is equal to minus root 3r. And for some value here, these two will intersect. Is it that they'll intersect? I mean, it doesn't matter that they will intersect. Of course they're going to intersect because this line extends off infinitely. The point is that the angle of this line is defined by this negative root 3. If you were to try writing this in cylindrical, the problem is you'd have to be integrating over this weird shaped region. And you can notice that there's a bit of an overhang, which I think is accurate, although I think I would need to sketch this more accurately. I can probably use Mathematica for that. Let me do that, and then show it to you, but I'm fairly sure this is correct. How do I draw this? Contour plot, I think. Contour plot, 25, and also z is equal to minus root 3r. R from 0 to 5, z from 0 to 5. Not from 0 to 5, r from z from minus 5 to 5. Ooh, that doesn't look right. One second. There we go. So this is what these two things look like if drawn accurately. So you have the circle and you have this line. The region that is being specified is this circular sector going from positive z down, I believe, because it's talking about the region inside the sphere and inside and here. So it's inside of this and that. Yeah. The y greater than or equal to 0 is only defining the particular part of theta that is used. So we can view it from the side and we have this, and then just end up rotating it by some amount theta to define the solid region. So this is not something I would want to describe in cylindrical, since, well, I mean, maybe you'd have to cut the integral. If you were to try doing it in terms of cylindrical, maybe you'd have to cut the integral here at whatever this value is for r, because that's where you have an upper function defined by the circle and the lower function defined by the line. But then there's a change in the behavior over on this end. So it is not too natural to do this in terms of cylindrical. It's more natural to do this in spherical. So spherical, I don't know, cylindrical looks bad. that's I don't know what else to say. Cylindrical looks bad. And I mean, this is definitely a three-dimensional thing, so polar is immediately not an option. All right. so okay, let's deal with that because that's the easy thing. So x and y. Y greater than 0 means this, which means that theta is from 0 to pi. So we have bounds on theta. Um, this region is what we're after. So r goes from 0 to 5, or rho, rather. Rho goes from 0 to 5. So we can see that immediately. In terms of describing this. So we have bounds for two of the variables. The third variable is phi, the angle of declination. So I need to describe, let me use another color, I guess I'll use red. I need to be able to describe this angle. Okay, so what is this angle? Um, hmm. There's probably a way to do it involving. I'm forgetting how exactly one does this. X squared plus y squared does something. Is rho squared sine phi. X squared plus y squared is rho squared sine phi. I think that is a way of doing this. The other way is just kind of thinking about unit circle values. So the point is that this quantity ends up being rho squared sine of phi, but all inside a square root. So rho sine phi. I really, but the thing is, I don't want rho there actually. Does rho have to be there? X squared plus y squared. Rho squared. Ah, okay, and z is rho cosine phi. Okay, yeah, that is also a rho. Yeah, so I know this is a technique that is used. Did I copy that right? Z is rho cosine phi. Yes. Okay. So that is converting this bound of the region into spherical, which is describing this line. And, well, rho is going to be some positive value, so we can cancel on that, and then we can move things to appropriate sides, and we end up with that quantity is equal to tangent of phi. Okay. Right, so the negative means tangent is in the second quadrant. This value is root 3 over 3. This is the pi over 6. What is it? It's a 30-degree angle in the second quadrant, so it should be 5 pi over 6. Phi is equal to 5 pi over 6 is this angle. Does that make sense? So root 3 for the slope. So if you go, it's like if you go over 1, you go down root 3. Let me think about it that way as well. Because the initial thing I wanted to do was actually use trigonometry to figure out this value just by considering this triangle. Okay, so yeah, so tangent of this angle is, or inverse tangent of root 3 is going to be pi over 3, a 60-degree angle. But then wait, a 60, yeah, and then, but then plus pi over 2. So it's pi over 2 plus pi over 3, which gives you 5 pi over 6. Right. So indeed, this angle is 5 pi over 6. There's a 30-degree angle here that's missing. Okay, I'm happy with that. So this has given me bounds for phi. Phi ranges from 0 to 5 pi over 6. Okay, so in total, this is actually a spherical box. This region is a spherical box. So what we can do to express E, we'll express E in set builder notation. So it's rho phi theta, rho phi theta, where rho ranges from 0 to 5, where phi ranges from, I guess it's easier to see theta. It's fine to leave theta last because that's just a rotation about the z-axis. Where 0 less than or equal to phi less than or equal to 5 pi over 6, and 0 less than or equal to theta less than or equal to pi. Okay. So I'm going to box that as the answer. Trying to do that neatly. Okay. Adjust it a little bit. There we go. Right, so that's 5a. Took a while. This triple integral. Okay, so we integrate x, and we have to convert x to spherical, so that's whatever that function is. And we have this spherical box, so that makes the integral not too bad, I think. So first, oh, maybe one thing I should also do now that I've noticed this, I need to double check that ooh. Okay, I think I made a mistake here. Let me pause this. Right, okay. Let me just check things over from the beginning. So, I noticed that there's a slight mistake with, well, a bit more than slight, I suppose. So, in number 2b, we did this integral. So the volume integral is correct here, but because we're working in cylindrical, we have to include the Jacobian, which I forgot. So that's a very silly mistake on my end. So that's going to change things quite a bit. This function is going to be the integral of r. So which the r pulls out, but you still have to evaluate z from 4 to r minus 4. This is going to how do I want to do this? So 4r minus r cubed is the function being integrated from 0 to 2 dr. Okay, and so when we integrate that, then this is different. This is going to be 2r squared minus r to the 4 over 4. Evaluating at 0 is still 0. Evaluating at 2 is going to be something different. 2, 4, 8 minus 2, 4, 8, 16. 16 over 4 is 4. Okay, so now the calculation is even simpler. That's a bit surprising. Okay, so 4 divided by 2 gives me 2 pi. Yeah, I don't like that. Okay. Alright. Maybe I can just quickly also double check the integral from here. So let's see, this was that problem. Plug in r instead. Yeah, 2 pi. Okay, so the integration work is correct. I just messed up at the very beginning with this Jacobian that I forgot about. So that's the kind of problem. That's the kind of mistake you don't want to be making. You don't want to forget the Jacobian. That will screw up all of the end result, and it'll be hard for me to, for either of us to give partial credit. We could give some partial credit, but maybe it's like going to be a third of the whole problem because you really want to have the correct integral that you're actually computing. Okay. Right. So all of that was because I noticed that this has a Jacobian, which is kind of bothersome in spherical. I need the formulas for x. Gosh, this is annoying. So the formula for x, maybe can I just print screen this? Grab it. Copy. I'll just paste it somewhere. Paste it over here. Oh, that's kind of big. Okay. Right. So x is actually rho cosine theta sine phi. And then we have the Jacobian to take care of. Rho squared sine phi it's fine to use the standard order because this is a spherical box. D rho, d phi, d theta. So in that case, then this integral, theta runs from 0 to pi, phi runs from 0 to 5 pi over 6. Rho runs from 0 to 5. Okay. But you can see that this is a spherical box, right? All of these are constants, and the function itself is a product of functions that can be separated in terms of rho, phi, and theta. So we may as well write this as a product of 3 integrals. So collecting the rows together, we get rho cubed d rho ranging from 0 to 5, multiplied by the phi. We have a phi squared. Oh, okay, that's a little bit bothersome. D phi. Phi ranging from 0 to 5 pi over 6. And theta. So theta ranging, there is a theta in here. It's cosine of theta d theta. Theta ranging from 0 to pi. I think that's just 0. Because cosine, it's really weird if that's the case. Cosine does this, right? And it's negative at pi. It comes back at 2 pi. So when you integrate cosine, you get 0. So I think that this ends up being 0, which makes the whole problem equal to 0. Sine at pi is equal to 0. Sine at 0 is equal to 0. 0 minus 0 equals 0, yes. Okay, well that's rather lucky. I would say don't expect that to happen on the actual exam problem. Most likely on the actual exam problem, you will have to do some of these evaluations. So it was just particularly nice that theta ranged from 0 to pi. If this was instead like pi over 2 to 3 pi over 2, this would be a non-zero value. I think it would be 2 or minus 2, depending. So it's quite possible that this could be non-zero. This is certainly not going to be non-zero, and you can evaluate this. The one comment I want to make is whether or not you know how to integrate something like sine squared or something like cosine squared. Let me just quickly check whether you're given any reduction formulas. I would expect not. Yeah. So these kinds of basic trig integrals are things you learn in Calc 2, but the way that you're usually taught in Calc 2 is to use reduction formulas. If you're not given reduction formulas, you'll be completely stuck, unless you know this alternative technique. The um, so just in case, the way that you deal with this kind of integral I'll mention to you is to use versions of the double angle formula. So cosine of I'm gonna use, well, I'll use x. Okay, make it look like a trig kind of thing. So there are various double angle identities for cosine, and the ones that'll be useful for these kinds of trig integrals are 2 cosine squared x minus 1, and also 1 minus 2 sine squared x. These are two of the three ways that the double angle formula for cosine is written. Now, what you can do with this is by rearranging, solving for the cosine squared or the sine squared, you're able to reduce the power down into just having a 2 in front of the variable, and that's useful because you'll be able to integrate the result. So notice that by rearranging this, and this is how I remember these formulas, because otherwise I wouldn't be able to remember them. We would get a 1/2 on the outside. We get a cosine of 2x plus 1 is equal to cosine squared x. This equation gives me that 1/2 of, let's see, I think it's 1 minus cosine of 2x. Move that divided by 2 is equal to sine squared x. Yeah. Just double checking. Yes. Right. So yeah, these are the reduction formulas that you can use basically. So using these, you're able to reduce even powers of sine and cosine, which is the one thing that you're missing for these kinds of trig integrals. So with that, you can rewrite the sine squared into an expression that you can integrate over. You'll be able to integrate this with respect to x pretty easily and do the evaluation. So in case you have a problem where it's like sine squared, it would be terrible if it's sine to the fourth. There ends up being algebra used to, like, you'll have to use the reduction formulas twice in order to bring it all the way down, and you'll have like a cosine of 4x in such a circumstance. It can happen, but usually it would happen on the homework problem rather than the test problem. Right. Okay, so I guess that's all I have to say about this, right? So convert, once you have the domain figured out, you convert over the function, you convert over, or you remember the Jacobian, then you do the integration, and here we lucked out, but most likely that's not going to happen on the exam problem. I would be surprised if this simplification happens on the exam problem also. Just for sanity check, I'm also going to plug this into Mathematica. So we have a rho cubed cosine theta sine phi squared, theta going from 0 to pi, phi going from, I'll start with rho going from 0 to 5, and phi going from 0 to 5 pi over 6. Yeah, Mathematica says 0. Okay, good. I'm happy with that. Number 6. Double integral x plus y dA. R is a trapezoidal region with vertices given. Okay, so first I want to visualize what this region is. This region R, is this an xy? And we're given a transformation. X takes in uv and gives you back. Okay, so that's gonna be a little. So this is a little bit different than what I've done in the lectures, uh, and in the lecture example. So this is xy, and you know you have like a uv kind of situation, and that you want the map t to go from uv to xy. R is some region over here. I'm just gonna schematically draw it like this, and this should be some s. Right, that's kind of the picture you should have in mind about how these transformations work. Notice that t, like these x and y given, they are actually behaving like t rather than t inverse. They're mapping from uv to xy. The problem is that the points are in terms of xy. So in order to determine what s is, we're going to have to create like the inverse transformation, or somehow cleverly determine how you would end up with these points, like what inputs u and v will actually give you these outputs x comma y, which I think is not the ideal way of doing it. Probably the ideal way is to actually solve for the inverse transformation. Let's try to do an accurate sketch of this trapezoidal region, just to make myself happy. 2 comma 0, 1 comma 1. Oh, maybe I should make it a little bit larger. 1 comma. Wait, what? That's not a trapezoid. That's not a trapezoid. Maybe that's a mistake. I'll have to. I might have to check with Katie because this is clearly not a trapezoid. Well, I mean, if I don't think anyone defines. Clearly, there are 2 pairs of parallel sides. With a trapezoid, you should only have 1 pair of parallel sides. I believe that's part of the definition. Um, 0, 0, 2, 0, 1, 1, 1, negative 1. Okay, that's really bizarre. Let's see what happens when we create the inverse transformation. So, okay, so t given to us is like this. X is equal to 2u plus 3v, and y is equal to 2u minus 3v. So notice when I add both of these equations, the v's will cancel, and we're just left with 4u. So x plus y is equal to 4u, which gives me that u is equal to 1/4 x plus y. If instead I subtract the 2 equations, then the u's cancel and I double up the v's. So I get 6v is equal to x minus y. And solving for v, that gives me 1/6 x minus y is equal to v. Don't know if I like that. But these relationships are what I would call T inverse. Okay, so we have T inverse mapping the other way around. And you can see that T inverse takes points that are in x comma y and returns points that are in u comma v. So we have the inverse relationship there. Okay. So, well, let's try plugging all of these points in. So we plug all of these points into T inverse to figure out what are the corresponding points in the UV plane. So 0, 0, I can see that that gets mapped to 0, 0. Just to maybe make it more clear in case it's hard to see, this is what we're doing. Okay, that's something's going on here. I want to move this down a little bit. So we supply T inverse with a point x comma y, and it will return a point u comma v. Okay. We supply T inverse with the next point, 0, 2, and what does it give back? It's going to give you 1/2, comma, 1/3. Okay. If we supply 1, comma 1, so then u is 1/2, v is 0, and if we supply, is it -1 or 1, comma -1? What am I doing? 1, comma -1, plugging it in. So 0 for the u, and for v, this is going to become 2, so we get 1/3. Alright, what does that region look like now? Let's see. Come on. Okay, so uv, we have 0, 0. Oh, we have a square. Okay, so we have 0, 0, 0, 1/3. I'm gonna kind of exaggerate what 1/3 looks like. 1/2, which should be larger, and then 1/2, comma 1/3. Okay. So in the xy coordinate system, we end up having this tilted square, which is definitely difficult to integrate over. But under the coordinate transformation, we end up with this rectangle, which is easy to set up the integral for. That's the whole point of doing the coordinate transformation. Very good. Okay, so we have that. Now we need to convert this integral over. So this double integral x plus y dA over the region R. So I'm going to call this guy S, and this is R. So by the, I forgot what it's called, the change of coordinate formula, we will need to convert the function. Thankfully, that's given to us. X is given and y is given. Well, x plus y actually just simplifies really easily to 4u. Then we have the Jacobian that we need to compute. I'm just going to use this kind of naming. J of t, the Jacobian of the transformation. And it'll be du dv. We can pretty easily begin to specify that this double integral, because it's rectangular, You can see that I'm going to give myself some space for the Jacobian. So if I use this integration order, then du goes from 0 to a half, and dv goes from 0 to a third. Let me move that s a little bit higher. Okay. Yeah, and we're just missing a little portion here that I'm going to compute off to the side now. So the Jacobian of t is the collection of partials. So we're using t, not t inverse, which means that we have x sub u, x sub y, or not, x sub u, x sub v, y sub u, y sub v. Computing that gives us the matrix 2, 3, 2, minus 3. Looks right. And that's going to give you minus 6, minus 6, for a total of minus 12. The Jacobian is in absolute values, so this is going to be times 12 here. Right. So to reiterate what I said in my lecture, the fact that the Jacobian is negative implies that this transformation is orientation reversing. There are some, I would say, more advanced textbooks where instead of the Jacobian being in absolute values, the absolute values are not there, but instead there's actually a flip in the parameterization. So instead of this going from, say, this direction, you end up maybe u going from greater to smaller, or maybe it's v that changes. Something ends up being flipped in the parameterization of the region, and so then you end up having two negatives which ultimately cancel each other out, which is why it's totally fine for us to just put absolute values around the Jacobian and integrate over the region in the standard manner that we would think of, in the positive manner, I suppose. Okay, let's compute this integral. I want to make it clear that this is multiplication. That doesn't look like multiplication. Okay. Right, so 48 gets pulled out of the double integral. Also, this can be thought of as a product of two integrals since it's a rectangular region and the function is easy to work with. So the integral of u du, u going from 0 to 1/2, multiply the integral from 0 to a third, the function 1 dv. Okay, now let's go ahead and compute that. Oh, nope. So it'll be u squared over 2 evaluated from 0 to a half. The other integral is just going to be the length of that interval. I'm going to simplify things. How am I going to do that? So the way I would think about this, okay, I mean, it's fine because I can just plug that in. So 48, plugging that in, that's just going to be 1 over 8 times 1 over 3. This cancels and gives you 6. That cancels with the 3, giving you just 2. Okay, trying to think about whether I could have possibly made a mistake anywhere. I would think not, but I'm not 100% certain. Let me just see things. Parameterize. So x plus y, where xy runs from its parameterization. The function x 2u plus 3v, fifth 2 minus 3v, ranging from 0 to a half, v ranging from 0 to a third, gives you the value 2. Okay, Mathematica agrees. I'm 90% certain. Okay. Number 7, and I think that this is a bunch of short answer problems that make up the last part of the exam. Okay. Give an example of a region that is type 2 but not type 1. Write it out, don't just graph it. Okay, okay. Type 2 but not type 1. That's... Well, let's start with graphing it because pictures always make more sense to me. Doesn't look straight. Bothers me. Okay, that really looks crooked. I don't know what's going on. Okay. How do I want to do this? Well, I kind of want to just have like this, is that good enough? If I do like that. A parabola that's offset? Well, I mean, the issue is you can describe it as a type 1 region if you split it. Well, to make it really bothersome, what we can do is maybe define like a sine function up here. Maybe I can... That's usually something that's doable. So, how do I want to do this? Maybe something like this as a lower function. I'm having difficulties with describing it easily. Maybe at 2 minus 2, so this will be the line y equals minus x. But if I'm viewing it with respect to y, then I should probably be thinking of this as something like x equals minus y. And I guess I should also comment that there's definitely an infinitude of possible answers for 7a. So you should feel free to come up with your own examples and try to come up with a few different ones, just so that you have like a experience to be able to, I don't know, create pick from like a variety of examples. So don't just copy me. So this region that is type 2, this here, and then some sine bits. I'm worried about the intersection. You know what? Let's make it even easier. That region. Why did I put minus 2 there? 2. But have it actually look like a sine function. So 1, 3, it starts here, it goes, sine increases, then decreases. Okay. And then increases, and then decreases. Well, it does this kind of thing. So let's just, this marks one period, let me make it mark another period. And so this is the value 2 pi y-axis. So too bad I'm drawing all over things. Is that, wait, no, that's 4 pi actually, because it's 2 periods. 4 pi, this is 2 pi, going down, up 1 period, up. Oh, wait, I went too far. This is the other period. 4 pi. Gosh, this is... I don't know why I'm just all of a sudden having a hard time drawing. Well, I usually am not good at drawing, actually. Up, down, back, up. Boom. Just looks funny because it's tilted sideways. So yeah, this is the sine function. X is equal to sine of y plus 2. Right, we shifted the sine function up by 2, but there's no phase shift in the sine function because it does exactly as it normally would. It increases in value, then decreases, then goes back to then zeroes out. Although 0 for this function is 2 because it's been shifted well, vertically with respect to the y-axis, horizontally viewed like this. So this region, how would I describe it? Oh boy. I really hope that doesn't. Make sure that the recording is okay. My computer's memory is maybe being a little bit finicky. Oh boy. The collection of points x comma y where 0 ranges from, or well, no, y ranges from 0 to 4 pi, and where x, so because I'm trying to define, come on. Alright, I need to restart. Okay, hopefully there's no video corruption. So, just had to restart OneNote, and I think that I was able to recover the rest of this problem. So, yeah, again, this is the sine function with 2 periods, flipped vertically, so that's a type 2 region. And this is how you would describe this region symbolically. So y ranges from 0 to 4 pi, and then x ranges from 0, right, that's this y-axis line, x between 0 and the function, the sine function, sine of y is equal to 2. So that completely captures this region that I've shaded in blue. Okay, so that's part A. The next part B, write out the extreme value theorem. Oh, okay. Well, I mean, there are some technical details which I might not completely remember either. But the main thing is that a continuous function on a closed domain contains its absolute min and max values. So if f x y, I don't remember if it is specifically two-dimensional. This theorem generalizes, if I remember correctly, to just arbitrary dimension, but well, let's stick with dimension 2 because I think that's what we're all experienced with. So if f of xy is continuous, it might be specifically on a closed and bounded set. I don't remember what exactly the set is defined to be. I think the book uses D. I taught in a previous course where the set was denoted by omega. You can just use a letter that makes sense. If the function f is continuous on a closed bounded set D, then f attains its minimum. I'm going to abbreviate this. Its min and max values on that set D. Right. So attains means that there are specific points on D where f takes the minimum value and the maximum value. It's not the case where you can get arbitrarily close to some point not on D where the function would have a maximum. That kind of limiting point would be an open point. It would violate the condition of the set D being closed. or possibly of it being bounded. If the point ends up needing to run off to infinity, that would also be a problem. So, if I was to, and I'm probably going to need to double check this just to make sure that the phrasing is accurate. These are like technical considerations that, depending on who grades or how the person grades, like you can be extremely picky or you can be kind of hand wavy about how precise you need to be. But I would say for sure you need to be talking about a closed bounded set D. You definitely need these conditions, closed and bounded. Is continuity the main condition? So we've had theorems that use like, well, first derivative continuous, but I don't think that was there. Partial derivatives existing or something. I'm pretty sure that the main dependency is that the function f is continuous. And you definitely need to mention something about attaining minimum and maximum values. So I would pretty much, I think I would phrase it like this, unless there is some mistake in the phrasing, which I'll have to check later. Okay, part C. Let's see. The area of region E is 2. This triple integral is 3. What is the average value? Okay, okay. Right, so this just requires you to remember what the definition of the average value of the function on the domain is. So you should remember that it's the triple integral of the function. I guess specifically it's over E, but then you divide it by the volume of the region E. Word choice is incorrect here. This should say volume. I mean, the analogous notion of area in 3 dimensions is volume. So, like, in a sense, like, this is area per se, but I mean, it should say volume. Okay, so this is the definition for the average value of the function over a region E, and you're given that the volume of the region E is 2. That is the denominator here. And you're given this triple integral's value. It's 3 there. So, well, that's all you need to do, really. You probably, to answer this statement, you should write down the definition just so that it's abundantly clear what you're doing. You're not just randomly sticking numbers together into a fraction. So you actually know it's integral of the function divided by the volume. Okay. Part D. If I set up this integral, what is the problem with the integral setup? Yeah, so notice that I'm not sure if this is ever possible, because notice that z ends up depending on x and y. So z is inside of x, which is fine. Z is inside of y, which is fine. But y ends up depending on z. So you have this kind of cyclical dependency, which is not possible. So I guess I would say like that the y integral on z and the z integral depends on y. My handwriting is a bit sloppy. Cyclical dependencies are not allowed. which is the issue. So the fact that you have z depending on y and y depending on z, that is the problem here. In order for the integral to be doable, you need it so that all of these integrals are evaluatable. But when you have this y integral that ends up depending on z, the result is going to be some function of z, and it's very weird. This expression is very weird because you have this depending on z. Possibly it's meant to suggest that like this is a typo. Like the one way to resolve this would be if this z was instead an x, right? So y can depend on x, and this would be fine. I don't think that this makes sense as a region. Like I'm trying to visualize what this would even mean. And yeah, no, it doesn't make sense. It doesn't make sense because you can't figure out like what is the to define this integral, you need like what is the maximum z value. Well, that ends up pulling you inside the integral, and you still can't see what is the maximum z value. So it's not a well-defined region. So maybe another way you could write the issue is that the region being integrated over is nonsensical. Like if you think about this integral as symbolic symbol pushing, like that you can technically do it. It's just that you'd have to view this z as not being the same as this inner z. Like this is some other variable, like you could make it t or something like that. Then in a sense, yeah, okay, it can be doable. Like I could feed it into Mathematica and it would give me an answer. But like as a human, you look at this and you should realize that like yeah, this region doesn't make any sense. This, yeah. So I don't know. There are different ways of expressing the issue with the statement. Okay. Okay. Last part. Is this last part? Yes, last part. Suppose you want to integrate over that, or you want to integrate this function over this region. So it's a rectangular region. Which is less steps? Integrating with respect to x first or y first and y? Okay, well, I'm pretty sure we've seen a similar problem in the lectures on this. So it'll be, what do you mean by first? I'm going to take first to mean the inner integral. So x first is easier. And I'm just going to specify the integration order being dx dy. Doing this integration order should be easier. And the reason is that if you do the x integral first, the y is going to be absorbed. All right, the outer y value gets absorbed. So the problem actually doesn't ask us to do the integration, so perhaps it would make sense to not actually compute the integral itself, but just to kind of phrase like what happens. So the y gets absorbed. So in particular, it's dx is simply going to be minus cosine of x y evaluated. So I'm just going to kind of abbreviate this. So x going from 1 to 2, means that we start off with x equals 1 and then going to 2. So that inner integral is easy to compute, and then this evaluation is easy. And then just as a point of contrast, the y trying y first. If I remember correctly, this kind of thing will involve. Actually, we can kind of just see it, can't we? So if we try to do the y integral, it's the integral from 0 to pi. It'll be y sine of xy dy. It will require, as you can see, this is a function. Well, if we just look at y, this is a product of two functions involving y, right? The function y and the function sine of xy. So if we were to integrate this with respect to y, this would require integration by parts. Integration by parts, which I'm going to just abbreviate here. So, which is certainly more difficult. It is theoretically doable. I believe the book actually goes through an example of this, and I think I opted not to in my lecture. But yeah, so the integrating x first is easier. Maybe I'll box that as my answer. And answering the y, I'm sort of contrasting, right? If I integrate with respect to x, I can easily do that. I can even just do that in this line here. But if I try to integrate with respect to y first, we can see this already involves integration by parts, and it's nasty, and I don't even want to start that process. So, all right, that's my answer for that. Okay, and yeah, so oh boy, if there are any mistakes, I will link to a follow-up video that corrects the mistakes. And probably the other solutions, the types of solutions that I will make, they will they'll be more they should capture the corrections as well. Okay.